Oh, nice. Thank you for letting us know. Still teaching? Oh my God. Seriously? Oh, fun. Right. Good to know. Okay. Let's see. Yeah. Let's go to the exercises. Let me see. Yeah. Let me still stop recording. Yeah, because that's our class rule that no, only the lecture notes are recorded, but the exercises are not. Okay, so let me share my. I guess I can share my whole screen. So it's actually let me still just share the lecture notes, but let me stop recording. Stop recording. Yes, I will stop record. Okay, let's see the questions, exercises. Okay, so the true or false. The set of all strings that can be composed or can be derived from the grammar is its associated language. Okay, that's true. Okay, that's the definition. Two grammars are their equivalent if they both are regular grammars. Okay, nice. Because they are different type of regular grammars, right? So only thing that's the only condition make them equivalent is that they have the same associated language. Okay, so this is the fun part, right? So all linear grammars are regular grammars. Okay, nice. Okay, the linear is a broader concept. Okay, so all regular grammars are left linear grammars. Okay, nice. That's false. Okay, because the grammars can also be may also be right linear. Okay, and also the regular grammar is a broader concept than left linear or right linear. And so all left linear grammars are regular grammars. Okay, nice. So this is true. Okay, because that's the definition. All right, so the regular grammar is either left linear or right linear. So if it's a left linear, then it must be a regular grammar. Okay, so PDAs can recognize all languages that produced by regular grammars. Okay, nice. Okay, this is true. Okay, that's true. Okay. So regular grammars produce regular languages, and the regular languages, of course, can be recognized by PDAs because regular languages is a smaller concept than context-free languages. Okay, so yes. And let's see, all context-free grammars produce regular languages. Okay, that's false. Nice, because context-free is the broader concept. So the language that can be produced by context-free grammar may or may not be regular, because context-free is the bigger concept or the broader concept. Context-free grammars may produce regular languages. Yeah, that's true, because the context-free is the bigger concept. Okay, so if a language is context-free, then it may or may not be regular. Okay, so yes, so may produce regular languages. All context-free grammars produce context-free languages. Yeah, I think that's true. That's yeah, that's true. That's true. That's just the condition, the definition. Yeah, the part of the IFF. Yes. Let's see. If a language is context-free, okay, then there exists a left linear or right linear for it. Okay, nice. So again, because context-free is a bigger concept, right? So left linear, right linear is associated with the regular, right? However, the context-free is a bigger concept than regular languages or regular grammars. Okay, so the context-free, a context-free language may or may not be regular. Okay, so these two are correct. Okay, all others are false. Okay, so again, for these kind of questions, just refer to the diagram, right? Okay. Yeah. So basically, you know, if something that fits the category of the smaller concept, then it must also fit the category of the bigger concept. Okay. Still, you can just view the like human being versus man or woman. Right? If you are a woman, you must be a human being. If you're a human being, you may or may not be a woman because human being is a broader concept. Okay. So anyways, you can refer to the diagram for it. Okay. And let's see. So first of all, any of all of them, they are context free, right? So any of them, all of them are context free. Okay, and let's see. So is this left linear, right linear? Is this regular? Is this linear? Any thought? Okay, nice. Okay. And actually, I just because I want to have more time to cover more questions. Therefore, all these are all linear. Right? They are all linear. All these three, they are linear. Yeah, all these three, they are linear grammars. Okay, so we're just seeing if it's regular or not. Okay, so for this one, it's linear, and every variable is on the left, so it's a left linear, and therefore it's also regular. Okay, so what this one? Okay, nice. So for all the variables, it's on the right. Right, so it's right linear, and of course it's regular. Okay, so what about this one, the last one? Nice. Okay, because it's not right linear or left linear, therefore it's not regular. Okay, so this is on the right, this is on the left, this is on the right, right? So it's only linear and context free. Okay, again, the linear grammar is a bigger concept than the regular grammar. Okay. And this one we'll kind of already cover in class, right? This is the same as exact 1A. It is 1A, exact 1A. Okay, and then let's do more fun activities to write grammars. Okay, so for this one, any thought? Okay, nice. All right, so basically we're repeating two A's, right? So remember when we're repeating one A, that's AS. Now we are repeating two A's. Repeating two A's any times, and no, it can be lambda. Right. So the same idea for 3A. This means that we need to repeat 3A's. Repeating A, S. Okay. You can also further to say 4A, like 5N, etc. Okay. So this will be pretty straightforward. Okay. And let's see, what about this one? Okay, nice, perfect. So for this one, it's every 2 A's we have 1 B. Okay, for every 2 A's we have 1 B, and the order is always A's first, then B. Okay, and we can also have lambda because it can be greater or equal to 0. Okay. So the difference between these two, for this one, you have 2 independent parts. Right, so you can write it as AB. Right, the A part can be 2 A's, and the B part can be any number of B's. Right, so note the difference between these two. Right, for this one, it's restricting that for every 2 A's we'll have 1 B. For this one, there's nothing restricting their number. Right, only restricted that we have A's first, then B's. Okay. So let me just double check the time. Okay, we have time. We have enough time. Yeah. Let's see. Contains at most 1 A. And our alphabet is A or B. Okay, nice. Okay. At most 1A, it means that either 1A or no A. Okay. So we can just do a direct translation kind of, right? So we can say B means a number of B's. Okay, so that's no A. Or we have 1A. Okay, and the B here means any number of B's here. Okay. Yeah. Just by the way, if you, so this is not a regular grammar, right? But no, this is a regular language, so you should be able to find a regular grammar for it. Okay. I guess I can just leave it as a exercise for you to think about how you can simplify this this rule so that it only have one variable. Okay. So at most 3 A's means that we can have 0A, 1A, or 2 A's or 3 A's. Right. So just write out all possibilities. Right. 0A, 1A, 2A, and 3A. B, A, B. Right, that's at most 3 A's. Okay, and then you can extend this to at most 4 A's, etc. Okay. Okay, so that's at most. What about at least 1 A? Okay. There's actually a more, I guess, more straightforward one. So let's do think about a direct translation thing. All right. So let's see. So S can be defined as remember for at least one A, we can start with any number of B's, right? And we have at least one A. And the rest of thing doesn't matter. I don't know. Let's just call it W. Doesn't matter, right? And the first part can be any number of B's. And the last part can be our anything, right? So remember, this is our anything's representation. B, W, and okay, so that's our direct translation. Okay, and the basic same idea, we can also do at least 3 A's, etc. Right, so at least 3 A's, it means that we have B A W. And that's at least 3 A's. Okay, and also you can just have the same idea, extend forward. Okay, extend to other ideas, right? So basically, just you can just do a kind of direct translation from the set builder version to the grandma version. Okay, but I guess this one is fun. This one will be harder, little bit harder, just a little bit harder. If we want the length of string to be even. But I guess you can refer to this one, right? So this is even number of A's, and we only have A's, right? So now we have A's or B's. So what can you do? Okay, I think you're having the correct idea. Okay. Yeah, actually, I think this one is correct, but I'm not positive. But I think so. Let's see. For this one, let me just reply here. What about if start with A, B? Okay. So basically, you can just have combinations of A's and B's. Okay. So if we want to 2 letters, and the letters can be A or B, what we can have AA, AB, BA, BB. Okay. Therefore, it means that the S, we can have AAS, and we can have ABS, we can have BAS, we can have BBS. And because we want a even number, so it's lambda. Okay, and then also you can kind of refer to our strategy when we write the rejects. All right, so A or B, and then we're repeating this any times. Right, that's the rejects version. Okay, so we just write it out because A or B means it's either AA, AB, BA, BB, because that's all possible combination for like 2 letters. Okay, and also because we can use those rules recursively in any order. Okay, therefore we'll just keep repeating like two letters. Okay. Or what you can do is that you can also say is equal to I don't know code A S, where this A can be either A or B. Right, so these two are equivalent to each other. This one just write all possibilities, right? But this just saying, okay, each part can be either A or B, but they are the same. Okay, again, the strategy also is the same as when we talk about the rejects. Okay, so that's even number of a even number of letters. So what about if we let me see the chart. Okay, so what about odd number? So what if the length of string should be odd? What can you do? Nice. So in other words, the last part, instead of it's not lambda anymore, it can be either A or B. Right? We just want one thing. We just want one thing. We just want one actual letter. So you don't need the S. Okay, because we just want one actual letter. That's it. Okay, so if you're using this part, means it can be either repeating anything, like just twice, or just have one A or B. Okay, actually, let me try to write it more clear. Let me see. Let me have a whiteboard. W, yeah. Let me see. So suppose we have is even. Then we have the S, either AAS or ABS or BAS, BBS or lambda. Alright, so that's W is even. Okay, so if W is odd, actually, I don't know. Is it possible to? No, it's not. It's not possible to copy that. So I guess I need to type again. So if it's odd, the first part is the same. ABS, BAS, BBS. But instead of having lambda, we need a actual thing. It's not enough. Because the first part only have like even number. We need to add one thing to make it odd number. So we can add either A or B. Right, so that's when when length of string is odd. Okay. Yeah. Or we can just say S. No, let's AAS and the lambda. Okay. And this A can be either A or B. Right. Again, these two are equivalent. You just write out each possibility. Okay. So similarly here, that means that S can be AAS and AA, right? And where A can be A or B. Okay. And these two are also equivalent to each other. Right? This version is write out all those possibilities, and this one just kind of summarize the possibilities. Okay, so that's even and odd. Okay, so I hope you know how to do it, how we can understand how to do it. Okay. Let me see. I think it's already 45. Yeah, it's already 45. Okay. So in case you missed that, the assignment 12 solution, sorry, assignment 12 access code is context. Okay. So I guess we will call it a day. Thank you for coming, and I hope I can see you in person next Tuesday. Thank you. You too.